Our next speaker will be Dr. Geoffrey Fox. Let me quickly introduce him. Dr. Fox received a PhD in theoretical physics from the Cambridge University, where he was senior wrangler. Throughout his career, he held positions at many different universities. He received numerous awards for his research and teaching, and also he's supervising the PhDs of many students. Currently, he's professor and director of the Digital Science Center at the University of Virginia. And Dr. Fox is known for his work in high-performance computing. He aims to make supercomputing tools more accessible for researchers to support making progress on a wide range of global challenges. And in his talk today, he will speak about how AI, supercomputers, and cloud can come together. So please welcome Dr. Fox.
Okay, thank you very much for this invitation. And I'm afraid I only listened to the parts of the last talk. It's still quite early here, so it looks a very good symposium. So I'm going to talk about the how supercomputers and clouds might evolve due to the introduction of more AI into their operation. Well, this is my abstract. You already have seen that, and so I'll skip over that. So here is a list which we'll return to of sort of what you can think of AI and interacting with systems, where systems are the clouds and supercomputers and clusters and what have you, and edge systems and stuff like that. The first 4 bullets are what you might imagine. Well, the first bullet is simplest. It is that the system actually hosts the AI. So we heard, of course, about TensorFlow and PyTorch and things like that. That is, running those systems is an area where actually I spend quite a lot of time, and that it's very important, and it's pretty advanced and reasonably well understood. But then there's also the AI can be introduced into the sort of start of the system, and they can actually try to write the software. There's a rather famous activity called Software 2.0, which notes the role of data in effectively programming. But you can also see AI increasing its role in just the design of the CPU, optimizing storage and memory designs and things like that, and also designing the architecture of networks and the architecture of hardware, or the hardware of the network. So that's one. Those are actually 2 groups. By the way, the color scheme is that where there's a lot of work, it's sort of dark purple, and then the shade of the purple gets lighter as there's less development. So then we have a whole set of activities where AI actually is involved in monitoring and managing the system. So this is not it's outside the jobs, and it makes the system run well. And then there's some well-known activities like DevOps and AIOps. And also there's a lot of well-established work on actually using AI to optimize power usage and efficiency of data centers. So that's one group. Then the third group is possibly more promising in that you can get much bigger factors improvement in performance. That is AI actually running in real time to optimize the system. And we can divide that up into networks, job scheduling, where of course, you couldn't say that the current heuristics used in job scheduling are effectively a variant of AI, but I'm sure that there will be improvements there. Then we have a set of activities when after the job is scheduled to optimize the I/O, the use of heterogeneous computers, and the local area network. And then the final bullet, which I'll actually spend most time on, is AI actually inside the job. If you think about these as a stack, this is the either the bottom or the top of the stack, depending on how you look at it. It's inside the job, and that's where you can get the greatest performance gains. And then, of course, having all these bullets, we can imagine integrating them together with some presumably relatively novel operating system. And then we will get all this running on single nodes, single clusters, single supercomputers, single clouds, and then multiple clouds, supercomputers, and clusters. All right, so that's the vision of how we will continue to improve performance of systems. Here is a sort of picture of this pervasive AI. So we imagine that in this world, this future world, there will be this red line here, which is the actual pervasive AI. Because to make all this work, you have to have control of the AI integrated into everything you do, say the initial design to the operation. That operation has to go inside the job. So it has to interact with the data, which typically comes from the edge, or if it comes from a central repository from that. It has to interact with a heterogeneous pool of hardware, and it has to interact with a heterogeneous bag of software. So we imagine that this AI will be realized in this fashion with an operating system where AI is embedded into all aspects of it. So coming back to the past, I was sort of impressed one day when Microsoft announced they were building an AI supercomputer, because at that time in 2018, supercomputers were not typically used in AI. Now they're actually used a lot because people have realized how important, how suitable deep learning is for supercomputers. And but anyway, but at least Microsoft articulated this vision of a global AI supercomputer, and that is sort of a similar vision to the one on the previous slide, that there is a supercomputer which does AI, but it's also going to do more than doing AI. It's actually going to be AI. Of course, there's a slightly scary future where this global supercomputer doing AI, run by AI, actually decides to take matters into its own hand. But we'll leave that topic. So. So if we think about this AI, I added modeling to what Microsoft said, because we do need to run large-scale simulations, and we do also need, of course, if we do deep learning, we're building models for the data systems. So as it's global, that already puts into the discussion that we're going to have a collection of clouds, and in my opinion, clouds and supercomputers will soon merge. They're almost merged now. You can get the same capabilities on clouds that you can on supercomputers. Supercomputers are not quite as available as clouds, so that possibly is not reciprocal. But I think we're going to end up in a world where we just have HPC clouds, which are clouds enabled by HPC, because as far as I can see, we have to have HPC because we have big data. You can't really do big data without HPC. And then we have to make all these things into I mean, this will happen very soon, or is happening now. We need to make HPC technologies like MPI integrate with, well, Mesos is, this is an old slide. I see I have Mesos. That's now deprecated, but at least we used to have Kubernetes, Java, Python, C++ all running together. All right, so let's now look at these two concepts. HPC and systems for AI and vice versa. So this important idea was started by Jeff Dean from Google. He gave a wonderful talk at NeurIPS in December 2017 called Machine Learning for Systems and Systems for Machine Learning. And he gave examples such as optimizing parallel computing, learning index structure, data center efficiency. That's what I already mentioned. AI for the running the data center, and also AI to do what I would call auto tuning, replacing choices and heuristics in running jobs. So if we take this concept, well, instead of machine learning, we can use the term AI. And in fact, today, most often AI is in fact deep learning. And so you can, it's up to you whether you want to call it AI, machine learning, or deep learning in this talk. And then Dean used systems. We can use a set of systems in one world. We'd use the term cyber infrastructure. We could use HPC if we're in a supercomputer world, and we could use HP cloud or HPC cloud in a more general world. So I'll hopefully I'll use the compromise term HPC sys, which points out we're aiming at systems that support big data, so they have HPC capabilities, and they also are general systems, and so they include clouds. So we have these two concepts. HPC sys for AI, that's my first bullet on the original list of topics. That is using HPC and supercomputers and clouds to run AI. And it's obviously important. It makes all the data analytics run much faster, and it will make the actual AI controlling all these operations itself run very much faster. But the topic of this talk is largely AI for HPSys, which is a somewhat newer concept, or at least less well-developed concept, and and I will mainly focus on that. And as I said, this has been going on for some time. Even in this 2018 faculty summit, there was discussion of using AI to configure database systems and things like that. So that's auto tuning. So if I look at my recent work over the last 10 years, I mainly did HPC for AI, such as running deep learning on a GPU or custom chips. But if we now do AI for HPC or HPC sys, then I actually did an analysis with Shantanu Jha, my colleague I've done a lot of research with, and we found there were various categories, which I'll go into now. If we go to Supercomputing 2020, there were 2 Gordon Bell Prize winners, and they both actually used AI for HPC. They were one used AI to learn the multi-particle potential, and the other used AI to explore phase space. And the original work I did here was in 2019, and so given the rapid progress in all these fields, it's pretty much out of date, but at least has some reasonable ideas. And one thing I think we need to do is to actually make these ideas more broadly usable by producing examples and benchmarks and things like that. So if we look at AI for HPC sys or AI for systems, there are many types of categories of which which are listed here. One is using AI after the system runs. So that will be producing some visualizations and using AI to analyze those visualizations. So that's sort of AI after the system. I won't discuss that anymore. Another one which is pretty important, is what I could call AI control. Is some of these other bullets in the previous slide I had, where you use AI to control the simulations and control the systems. 2 I'll mention a bit more here is AI for auto tuning, and AI what I call around HPC systems. That's AI really embedded into the systems. And this will give you the biggest facts in general. If you look at how you integrate AI with systems, the more deeply you integrate it, the bigger the potential factor you can get. It's not too surprising. On the other hand, if you integrate it at a high level, say in the overall operating system, is pretty important because then it's valid immediately for all applications. Whereas if you have to put it inside the application, you have to do detailed application-specific work. So I won't spend too much time on this picture. It's a list of 8 categories we came across. 3 were in the auto tuning area. For instance, where we want to learn either the configuration of the system, or we want to learn how to run ensembles, what parameters to choose, or we want to learn the actual details of the model from the data. And then the other 5 are what I call AI around HPC sys. And then you have various possibilities as to how you use AI. One learns outputs when these outputs are sort of discrete numbers. Other ones learn broad distributions, fields. Others involve learning agent behavior. This category here, AI learning model details, is typified by learning how to run at different scales or learning effective potentials. There's also an interesting one involving data assimilation. All right, so here are some examples. So I say the simplest, a very important example where there's quite a lot of progress is AI auto tuning, which is using deep learning and other technologies to improve and enhance the classic auto tuning tools, and that's already going on, and there's several papers in that area. Here is there was actually now almost 2 years ago, there was a paper with this controversial title with speed up of 2 billion. And they actually changed the title to remove that claim, but they did get a speed up of 2 billion on the climate application. And it sort of captures why this is sort of interesting, namely, it is possible to get huge increases in performance. And this particular paper was interesting because it took a single AI surrogate, so they're just taking a simulation and then replacing it by a neural net. This thing at the bottom of the slide is the neural net this paper used, and it was they also they set it up so that they could run the neural architecture search on it to find the best architecture. But they then chose that best architecture, and it surprisingly worked on multiple applications. I don't think that's fully understood yet. Here is actually somewhat simpler example, which was the one I first did with some colleagues at Indiana University, and we took a nanotechnology simulation, which is a classic MPI, OpenMP code, and we used a simple multi-layer perceptron to learn the results of that simulation. And the input was the run was specified by 5 input parameters, and the output was a distributed field distribution, which we took as 150 parameters, and it was very successful. And the deep learning was far better than all other approaches. And you can see on the bottom right that here we compare various output measurements with in the validation and testing set with the prediction, and you can see the straight line suggests that the comparison is very good. I should note that this is pretty good for education because you can you actually get a speed up of effectively 10 to the 6 if you do lots of because each of these inferences is much faster than the original simulation. So education is interesting because that means you want to run the code a lot of times because every student will run it. And so that's a particularly attractive example for this. But even like General Electric uses this type of idea in their interactive engine design. They at least in the talk I heard, they run their computational fluid dynamics at night. That runs a couple of hundred different runs. They learn from those 200 runs. Then the engineer uses the resultant neural net to do their interactive design the following day. Here is an example of related idea to, if you look at actually drug discovery these days is actually getting more successful in the fraction of the explorations that lead to drugs I think is improved. And one of the reasons is they're using AI to learn from the specification of drugs and chemicals, the properties. And this particular news item had various claims, but this is just typical. It's not the only example of this. Here is another example, which sort of has some perhaps more controversial implications. So we took a classic molecular dynamics problem, which is just in this example here, 16 particles interacting with the Lennard-Jones potential. And we have 4 slides. If we look at these 8 diagrams at the top right, the diagrams on the left are actually the simulation, and the diagrams on the right are indistinguishable. They are the results of the neural net, which is as this is a time series, we learned it with a recurrent neural net, and it had a very striking feature. The recurrent neural net was able to take a 4,000 times longer time step than the original simulation. And that then implies a speed up, because to step forward in time, I can step forward much, much faster. So somehow this points out that the AI can actually learn fundamental theory, because we've replaced Newton's laws with a recurrent neural net. So you can imagine an AI system watching apples falling from trees and fitting them with this recurrent neural net and coming up with Newton's laws, or their version of Newton's laws, automatically. So the diagrams at the bottom right typify the difference in the errors. The error for the recurrent neural net, even for the large step sizes, is around 10 to the minus 5, whereas that for the classic numerical approach with simulations just breaks down even when the step size is 10 times as big as the 0.001, which is the one that works. An important example is, I say, smart ensembles. You want to run over phase space, and you need to design our best to run through phase space quickly. This is an important type of computation, which is done in both weather forecasting and drug discovery, and AI has been used successfully in that case. So if we look at, this is sort of abstracting what I already went through for these examples here, with if you have the computation defined by parameters, and that was the example I did with my colleagues at Indiana, then this is, you can replace the simulation by the neural net. Here is a sort of formula for the speed up, and so you can derive well-defined speed ups. And what it's important about this analysis, it tells you what's important. So what's important is the number of training samples compared to the number of inferences you want. You will only get, for obvious reasons, you only get good answers if your number of lookups, number of inferences, is large compared to the training sample. Now, the training sample, as I mentioned, was 200 for General Electric, which was probably not trying to get the most accurate answer. We find in most of the cases where we're trying to get accurate simulations, somewhere between 5K and actually it says 16K here. I would say we go up to 100K in some of our examples. So as we get these big factors here, like in the case of the nanotechnology, it was 10 to the 5 or 10 to the 6, depending on exactly how we state it. We can easily get zettascale performance by running on petascale machines or exascale. 10 petaflop computer multiplied by 10 to the 5 is a pretty fast computer. It's a zettascale. In some of our work, we do use agents. We use agents for modeling pandemics and agents for modeling virtual tissues, and then we can try to learn the agent behavior by replacing these agents by AI surrogates. And as we have a lot of agents, this is pretty good. So when you do an agent-based simulation, if you can really speed up the operation of the agent with AI, this is quite promising. I mentioned this example here where we use data assimilation, where we take an AI, produce a model such as a model organism, and then we adjust that organism to the data that's of a particular, in this case, particular patient or something like that. So we designed this. This is with my colleague at Indiana University. We designed a simulation surrogate-based system for doing virtual tissue simulations in general, and it involved multiple of these surrogate categories. Right, so those are relatively detailed slides. The rest are somewhat more general. So I'd already remarked that this idea of replacing jobs or simulations or anything, it could be data analytics, is broadly valid as far as I can see, and we need to extend the work which is in rather particular fields at the moment to make it more uniform. One thing I'm trying to do with an organization called ML Commons is to produce benchmarks and best practices to inspire work in other fields. If you look at the things like the drug discovery, I mentioned there's pretty well advanced. For large-scale simulations, we had that 2 billion paper, so we have good results, but it's not developed well. Agent-based simulations, there's not so much work. Learning potentials has been a great success, and actually using AI to guide ensembles is also very successful. Again, there's been the claims of dramatic speed up. Another example here, which I didn't go into, is learning microscale. Namely, if you do weather and fluid simulations, you have a lot of turbulence and clouds, which are microscale, which you can learn using AI, and initial results are quite promising. And I pointed out we can use recurrent neural nets to represent dynamics, which is effectively using AI to effectively learn theories. If we want to see how the future might go, we have this problem where we need 5K to 100K simulations. So the one idea which needs more investigation is that we can divide the simulations into classes, and we can learn meta surrogates for each class by running off a bunch of simulations and particular applications, and then use them for different applications. So you can imagine a sort of factory where we produce these meta surrogates, and then the actual computational scientists in the far right, they use those meta surrogates to produce results. As far as I know, this idea was not well investigated. So this 2 billion paper introduced neural search that is not quite understood why that how that should be used and how broadly that is, because they managed to join together some pretty disparate applications, quite surprising. So further work is needed there. We need work on uncertainty quantification, and we also need to try to optimize the choice of training set, because the challenge is we need to have a training set. We need to have a number of inferences which is large compared to the training set. So we need to reduce the size of the training set if we're going to make this successful. So if we look at this from a computer science point of view, there's lots of theses can be written in this area. We need to find out how we which of those 8 different categories are important, and how to look at each of them. How we can sort of ask what we can do with zettascale computing. And we also want to understand the difference between the surrogates for the whole job and surrogates for the parts of the job, such as the potentials. We need to, in some sense, redesign our algorithms so we can actually do this. So I pointed out this pervasive AI. Well, it only works if applications are designed so that you can use AI in them in a broad fashion. So we need to understand which is the best neural network structure. And I'm still a bit surprised there isn't more work in this area. If we think about this in running this sort of automatically, we're going to find cases where sometimes we can use a surrogate and sometimes the surrogate is not accurate enough. We have to rerun the simulation from scratch. So that provides certain, as there's such a huge difference in execution time, that will provide pretty difficult load balancing and job scheduling challenges. As I pointed out, we need a new operating system which allows us AI and simulations and data analytics to interact and with each other. All right, so let's, here's just one example I gave of some very exciting work in network engineering with ESNet, and colleague Mariam Karen, she and her colleagues showed how you could use deep learning and reinforcement learning to learn to basically manage networks. So that was one of my bullets, managing the networks. And these graphs here show how the shortest path algorithm is outperformed by the reinforcement learning, especially for the modest network nodes where it's going to run most efficiently. And on the right, it shows how the packet loss is decreased as you increase the scale of the reinforcement learning. So this type of activity needs to be extended in a much more pervasive fashion. Now, if we look at another bullet was AI ops and DevOps and things like that. So we need that. Those are already using AI, so that just needs to be increased and actually AI is typically not used so much in AI ops and DevOps, but it should be used more. And this plot here from Gartner shows this DevOps with all these different companies and concepts in it, but this points out how complex this field is. If we're going to use AI throughout all of this, then there are going to be lots of new areas we have to integrate it into all these areas. That's pretty complicated, and all these companies and vendors. So if we look at AI, one of my bullets was AI optimizing I/O, heterogeneous compute and local area network. So that includes the field of optimizing compilers, and that's an area I've worked on in the past. And I'm not so certain that AI will change optimizing compilers, but it's possible. What's easier to do is to optimize the execution time by, say, improving the communication. There's several papers on trying to improve the communication, especially in clouds with shared communication. And it's clear that AI can do a much better job there, and also can decide how to schedule and run. Right? So we also can do, and this is of course done now, we can optimize power use, not execution time. And we just need to integrate these ideas more pervasively than it's done now. I sort of point out that this concept sort of removes the difference between clouds and clusters and supercomputers, because those are largely different they also have the same hardware these days. They just differ by the way they're managed. But if we have AI managing them, it will actually choose the best way of managing them. So it will take the right mix of cloud and supercomputer and cluster strategies and run all the systems in that fashion. So here we are now finishing. So this just points out that this is sort of, if you like, this is my personal analysis of how to parallelize and use various systems, commodity clouds with low performance nodes, HPC clouds with high performance nodes, and how that maps different types of problems. And of course, AI has to be taught how some things like data parallel TensorFlow is actually pretty tricky. It's not as tricky as, say, running graph algorithms on a supercomputer, because so the actual algorithms are somewhat simpler. So we need to somehow teach AI all about these different concepts. So, as I pointed out in the original abstract, AI, and I mentioned a couple of slides, AI will make all systems HPC clouds, because it will just remove the usage difference. So it will then, it will go over these differences between the use of virtual machines or not, the user privilege, the shared networks in clouds, and the different allocation block scheduling and the more dynamic scheduling. So after we've done this, now we've got sort of an AI running every one of our systems. We can then go back to the grid computing ideas and try to federate everything together and link all the clouds and all the HPC clouds together. So to do that, we better use standards, and there are inter-cloud interoperability standards, but we all need standards at every level of the system. That's just a reminder of this picture. That's a reminder of those bullets. And here is the final slide. So I tried to show you that AI is a promising, pervasive approach to increase persistent performance, even as Moore's law declines. The largest factor, which can be billions, comes from the inner layers, but they're application specific. The outer layers are very important, but the increases are less dramatic. I try to discuss AI for HPSys in greater detail, and I try and we can get huge performance at a scale, and we need to work on the hardware and the software which supports this concept. And of course, if it really possibly can be transformative in terms of the types of applications can be run. And I try to point out that this will lead to a broad deployment of HPC clouds. And we need, of course, in computer science, we need some AI advances so that we can do the reinforcement learning in a broad fashion. So that's the end of my talk. Thank you.
Thank you so much, Dr. Fox. Very, very interesting to see. In the last talk, we spoke about how we can get more performance for doing AI, and now we're speaking about how we can, with AI, do even more computing.
That's right. They interact together.
Yes, very interesting to see. One question I had in my mind was, you mentioned during your talk that there's the need for a next generation operating system. Can you maybe very quickly elaborate what characteristics of this will be?
Well, it has to have this idea that there's an intelligent, what I call the intelligent ether, which is that the AI is embedded into every job. So let's take the example of the one I've done most on, simulations. We need to be able, in some sense, to speed up every function in that code. And rather than at the moment, we just do it by hand. We say, all right, we've replaced the potential. Let's put an if statement here to call the surrogate for the potential rather than the original. But in general, you ought to be able to imagine just replacing every function in a code by its surrogate. So that to make that work in a sensible fashion, we're going to have this operating system supports this pervasive use of AI with AI and non-AI versions of the codes running. And I pointed out that has lots of load balancing difficulties and things like that.
And will this operating system come from a research scientific background, or will one of the big commercial companies eventually?
Well, these days, commercial companies, when I started computing a long time ago, academia was typically ahead of industry. Now I'm not so certain that's true.
Ashok, what are your thoughts?
Yeah, I think the really, thank you, Fox, really fascinating again in terms of the approach. I think right now it's about what more could we do to actually squeeze out, and I think a lot of time we see the performance of systems really, are they optimal or not? And I think your concept of AI ops is something that we see, at least in industry a bit, where there is how it's getting deployed in terms of operations of data centers, but less so within the context of like overall systems of software and so on. But in order to do that, do you think like the approaches that we have around AI right now, just in terms of like deep learning was one that you mentioned, there probably need to be other advances as well? And
yeah, what I try to say at the end of one of my end slides is we certainly need tremendous advances in AI. And although today everything is dominated, well, at least most things I think are dominated by deep learning and reinforcement learning and things like that. Whether that's the right way to do it, we don't know, of course. So we will only do this by actually using the AI we have today more pervasively. And so I think it's there's going to be an interaction between the users and the developers of the AI ideas.
That's great. Thank you very much for sharing this. And I know it was quite early for you where you are, so I really appreciate you taking the time and the early start to share your thinking in this topic with us.
Thank you.